One area that interests me is calculus of variations, where we want to find critical points of functionals. For example, minimal surfaces are minimizers of the area functional. But first, before finding a minimizer, we must first know if one even exists. Here's a sufficient condition for a functional to attain its minimizer in a certain admissible class of functions. So if A is the set of functions, which I assume is Hausdorff, and I is the functional, if I satisfies the property that for any real number alpha, k alpha, which is the sublevel set of a u and a such that I of u is less than or equal to alpha, is sequentially compact, then we can deduce that I is uniformly bounded from below and attains its infimum. So the reason for this is if alpha naught is the infimum, by definition we know that there's some sequence that converges to alpha naught, or I of u, there's some sequence un such that I of un converges to alpha naught. And we can assume that this is strictly decreasing. Now, if Kn is the set of all u and a such that I of u is less than or equal to un, this set contains un, and k of n plus 1 is always contained in Kn, and it also contains, each Kn contains the tail of the sequence. Since K1 is sequentially compact, we know that there's some subsequence u sub nj, so that u sub nj converges to u in K1. Another thing is that since A is Hausdorff and Kn is sequentially compact, you can prove that it is closed. And this is enough to show that for any n, u is in Kn, so u is the minimizer. What this tells us is that in order to show a minimizer of a functional exists, we need some notion of convergence for the sequentially compact criterion. And this is exactly why in geometric measure theory we generalize surfaces to things called varifolds. Varifolds allow for convergence, or namely weak convergence, which allows us to prove compactness and in turn existence of minimizers. So this is just one area I'm interested in, and I'm interested in many applications of calculus of variations. Thank you for listening.